this video, we're going to take a look at the valence shell electron pair repulsion theory. We already know from our bonding lab that we did earlier in this unit that molecular compounds have very different properties. We saw that some molecular compounds have odors and others don't. We know that some of them can dissolve in water while others won't. We know that some have a lot higher melting points and boiling points than others do. So if we're going to try to figure out why they have different properties and be able to try to predict those properties, one of the things we're going to have to take a look at is the shape, because shape will play an important role in determining a compound's property. In order for us to determine the shape of a molecule, we need to use the VSEPR theory, the valence shell electron pair repulsion theory. This theory basically tells us that when you have atoms bonded around a central atom in a molecular compound, they're going to try to be as far away from each other in order to minimize the repulsions that their electrons feel. So as we work our way through the different shapes that molecular compounds can create, note that we'll be talking about this in relationship to how far away from all the other different atoms they are, because we know that electrons repel each other and want to try to be as far away from each other as they can be. As we work our way through the notes, you may find it useful to create a title with these headings on it, as we will be talking about these pieces of information, and note that these will also be very important for you in helping to predict what kind of shape it is that your molecular compound has. So starting out with our first shape, we're going to talk about compounds that form a linear shape. Linear compounds occur when there are two atoms bonded to our central atom and no lone pairs. And so examples that we would see here would be something like BeH2. So if we were to create the Lewis dot structure, we would have something then that looks like this. Another example that you would be familiar with would be something like CO2. So here is where you have carbon double bonded to two different oxygens. Note that in both examples, we have two atoms bonded to our central atom. So we have two hydrogens bonded to beryllium. Down here, we have two oxygens bonded to carbon. Note that they don't have to be the same. In this structure here, we also have two different atoms bonded to our central atom with 0 lone pairs. So all of these examples would create linear structures. In addition, compounds that are made up of only two atoms will also create linear structures. So something like maybe HF or two chlorine atoms bonded to each other. These would all be examples of linear compounds. Now, if we take a look at these shapes, we see that what happens is, in this example, our two hydrogen atoms are going to get as far away from each other as they possibly can around our beryllium atom. And we see that this happens when our bond angle is 180 degrees. In other words, our two hydrogens are 180 degrees away from each other. Note that if I were to continue moving my hydrogen atom further away from the other one, I eventually reach that point where I start moving it closer to it again. And so this is why they're as far away from each other as possible. We can also take a look at what's referred to as a ball and stick model. Ball and stick model is a way for us to try to visualize what is happening in the three-dimensional world, since molecules are indeed three-dimensional. And this becomes tricky as we try to write our three-dimensional molecules on a two-dimensional piece of paper. Linear is very two-dimensional. It's a very flat structure, and so we actually don't have very many problems in representing linear compounds on our piece of paper. So this would just be an example then of a ball and stick model. Moving to our next shape would be trigonal planar. Trigonal planar compounds occur when there are three atoms attached to our central atom, and again, 0 lone pairs. And when this happens, or examples I should say, would be something like BH3. And so if we were to take a look here, so far a lot of times we've been drawing our structures that look like this. Another example that you would have taken a look at would be something like CH2O, where you have an oxygen that is double bonded to a carbon, and two hydrogen atoms single bonded to a carbon. In both examples, what we tend to notice is while these guys are indeed 180 degrees away from each other, these two atoms are only 90 degrees, and same with these two. And so these are going to repel each other more, and it basically forces these two hydrogens to come down further. This results then in all of our atoms being 120 degrees away from each other, and so we end up then with a structure that looks like this. Again, note that our bond angle here is 120 degrees. This is also 120 degrees. This is also 120 degrees. And we call this trigonoplanar. Trigonal because it makes this nice triangle shape, and planar once again because we're a very flat molecule. And if we were to take a look at our ball and stick model, again, we can see that this indeed looks like a very flat model, and we see then that it also takes that nice triangle shape. Moving to our third shape, we create what's referred to as the tetrahedral. Tetrahedrals occur when there are 4 atoms bonded to our central atom, and again, 0 of them are lone pairs. Examples here would be things like carbon bonded to hydrogen, 4 different hydrogen atoms. Other examples would be silicon tetrachloride, anything that has 4 atoms around our central atom. And so again, if we think about what's happening, a lot of us are drawing pictures that look like this. And we're thinking, well, yes, this is 90 degrees, 90 degrees, 90 degrees, and 90 degrees. And while that's true, we also have to think in the 3-dimensional world. This atom to this atom is 180 degrees away from each other. And so because this is so much bigger than this, we're going to try to reduce that. And so when we do this, we create what's referred to as a tetrahedral shape. Whoops, I went to the wrong slide there. Tetrahedral shape. Here we see our bond angles are now 109.5 degrees. So you can almost kind of think about it as forming a little tripod along the bottom with one atom that comes up. Right, so now we're no longer looking at a flat structure here. Instead, every one of our bond angles is 109.5 degrees. This angle would be this angle, and this angle would all be equal to each other. And so we create this tetrahedral shape. Now this one becomes a bit more challenging for us to draw on a piece of paper. If we take a look here, we see that our atom is no longer flat. And so when we go to draw this on a piece of paper, we have to make sure that we account for that when we're drawing our 3-dimensional structure. So if this were to represent CH4, we would put carbon, say, in the plane of our piece of paper. And our hydrogen up here is also in that same plane. So we're just going to go ahead and attach our hydrogen like normal. We also could place one additional hydrogen like this one in the plane of the paper, but this time it's coming down slightly, so we're going to go ahead and include that slight angle down to show that this has that 109.5 degree angle. Now this hydrogen we can see is coming out of the plane of the paper. So if I were to create a drawing to show that, I may represent this by drawing a bold line. And this bold line here is going to show that this hydrogen is coming out of the plane of the paper. This hydrogen then would be going behind the plane of the paper. So to represent that, I would use a dash line to represent that it's going behind the piece of paper. And so this is the notation that we use in order to draw our 3-dimensional shapes on a 2-dimensional piece of paper. Now if we take that tetrahedral shape and we go from having 4 bonded atoms to only 3 bonded atoms to it, but now instead of 0 lone pairs we have 1 lone pair, note that altogether my electrons are going to take the tetrahedral shape. In other words, if we look at the example of NH3, ammonia, we see that we have 4 regions of electrons around our central atom. 3 of them are bonds, however, and 1 of them is a lone pair. And so altogether electrons will take the tetrahedral shape, but because 1 of them is a lone pair, the overall compound takes a trigonal pyramidal shape. And so if we were to take a look at what this structure looks like, we can see here that we have this tetrahedral shape again with our 4 regions of electrons. However, because this is a lone pair, when we actually look at our compound, we see we have a triangle on our base, and we create this pyramidal shape associated with it. And that's why it's referred to as a trigonal pyramidal shape. Now you'll notice that our bond angle here is slightly smaller than it was for a tetrahedral. This is because our lone pair of electrons here is going to sit closer to our central atom than a bonded pair of electrons would. And because this is going to be closer here, it's going to push these guys slightly together more so than what we would have had here. So this is going to be then the shape that we would create for our trigonal pyramidal compounds. And once again, we would create something then that would be three-dimensional. So you'll notice here then that we have something in the plane of the paper. So for example, your nitrogen to your hydrogen would be in the plane of the paper. One of your hydrogens would be coming out of the plane, so that would be the one we would want to represent with a darkened line, and another one would be going behind the piece of paper, so we would want to represent that with our dash line. And just like we could take and change the number of lone pairs around that tetrahedral shape, we can do the same thing as well with, we can change it once more as well. So if we still have 4 regions of electrons around our central atom, but this time we increase it to having 2 lone pairs, that means then we only have 2 bonded atoms, we create what's referred to as the bent shape. The most common compound that you guys are familiar with that takes the bent shape would be water. So water has oxygen bonded to 2 hydrogens, and there are 2 lone pairs around your oxygen atom. So again, we have 4 regions of electrons, and those 4 regions are going to take that tetrahedral shape, but this time 2 of them are going to be lone pairs. So here we can see those electrons taking that tetrahedral shape, but because these 2 are lone pairs, our overall compound ends up having a bent shape associated with it. And just like with our trigonal pyramidal shape, where our lone pairs are sitting closer to our central atom, pushing our atoms, bonded atoms closer together, the same is true when we have 2 lone pairs. These guys are both sitting closer to oxygen, and it's going to cause the 2 hydrogens to come in slightly. So now we've moved down to a bond angle of 104.4 degrees. Once more, however, we've now returned to a nice flat molecule, and so when we were to draw these on a piece of paper, we can go back to just simply using 2 straight lines. The next 2 shapes we don't come across very often. The first one's referred to as trigonal bipyramidal. This happens when there are 5 atoms bonded to our central atom and 0 of them are lone pairs. Examples here would be something like PCl5. So if we were to create the Lewis dot structure for this, we would create something that would look like this. Remember, phosphorus, because it's in the 3rd row, can accept more than 8 valence electrons because it has access to that 3D orbital. And so we would create a Lewis dot structure that looks like this. When we have 5 atoms around our central atom, we create this trigonal bipyramidal. Trigonal because our 3 atoms here in the center create a triangle, and then pyramidal because we create a pyramid up, bipyramidal I should say, because we create 1 pyramid up and we create 1 pyramid going down. So there's almost like there's 2 pyramids. Here are bond angles. Those that create the triangle in the center are going to be 120 degrees away from each other. So this would be 120, 120, and 120. And then the ones that go up and down are going to be 90 degrees away from the other ones. And we would create then a shape that looks like this. And the last shape that we'll talk about is referred to as the octahedral. Octahedrals occur when there are 6 atoms bonded to our central atom, none of them being lone pairs. Example here would be SF6, so we would have sulfur bonded to 6 different fluorines. Again, remember, sulfur is in the 3rd row and can accept more than 8 valence electrons because it can put some in that 3D orbital. So if this is what our Lewis dot structure looks like, we're going to create that octahedral shape. And here you can see what that octahedral shape looks like. In the center of our atom, we create this square between 4 of our fluorines, and then we have 1 fluorine that goes up and 1 fluorine that goes down. And creating then that ball and stick shape, we would create something that looks like this. So to recap, in order for us to predict the shape of a molecular compound, we need to know how many atoms are bonded to our central atom, and we also need to know how many lone pairs. And then we always need to keep in mind that atoms and electrons will repel each other and want to get as far away from each other as they possibly can, giving us the biggest bond angle.